Tim will look at IP over optics and use cases for ZR plus optics over an open DWDM line system to help reduce cost and enhance sustainability. So welcome to Tim, and if you want to share your slides, we're ready to go.
All right. Well, thank you very much for the introduction, Mike. And as he mentioned, my name is Tim Drake, and I am a consulting engineer in optical with Nokia. Been doing this for quite a while. I will tell you, I go back to the days where the fight was between erbium doped fiber amplifiers and fluoride amplifiers. So I've been in this for quite some time. So really what I want to do today is look at kind of a primer. I was told these need to be educational. So let's look at some modulation and Baud Rate. And then we'll look at, a real use case on how is it going to work in the middle mile? And do you really need this kind of bandwidth in the middle mile? And what we're really seeing is the answer is yes. With the federal BEAD funding, XGS-PON to the edge is becoming the de facto standard. And with that, you're starting to see 100 gig and potentially higher coming out of the GPON equipment. So we'll just jump right into it. So if we were to take a look at modulation and symbols, so going back and looking at your 10 gig transceiver, that was a simple light on, light off. So if it's bright, it's a 1. If it's a low light, it's a 0. Since then, with coherent technology coming out, we stole a little bit from the microwave era. So now we're doing quadrature shift phase keying, where we're now transmitting 4 bits per symbol. And you can go all the way up to 64 quadrature amplitude modulation. So when we look at this, really the more bits you can put onto the fiber, sadly, the bits get closer together. So your optical signal noise ratio goes higher, and you can only go shorter distances. So really, the fewer bits you put on your fiber, the farther you can go. And that also means that you're going to be generally running at a much lower bit rate. So if we were to just kind of look at it, QPSK is generally good at 100 gigabits, sorry, when you're running like 33 gigabaud. 8 QAM allows you to run 200 gig in a 100 gig space channel. 16 QAM allows you to jam that into a 50 gig channel, but at that point, you're starting to really lose some distance because of the noise limitations. Okay, so what is baud rate? Well, baud rate is really how fast the symbols are transmitted across the fiber. The higher the baud rate, the higher the modulation format, so the more capacity you can transmit. But we have to also go back and remember that the baud rate defines the channel size. And when I say the channel size, think back to your traditional WDM system. If it was put in 7 or 8 years ago, it's probably what they call a FODM, a fixed filter optical add drop multiplexer, which means that they're comb filters that limit the spacing and the width that the signal can be carried in across the fiber. In the case of a 100 gig space DWDM system, then it is an ITU standard to be either 40, 44, 80, or 96. At 40 and 44 channels, you're running 100 gig spacing. At 50 gig spacing, you are running either 88 or 96 channels, and that is just in the C-band. So what does that mean? Well, that really means that at 50 gig spacing, you're good up to about 100 gigahertz. If we were to run 100 gigabit per second line rate, that takes about 33 gigahertz of space on the fiber. So that will fit into a 50 gigahertz filter. And generically, filters are, again, comb filters, and they are not exactly flat. And when I say flat, there is a roll off on the lower and the upper edge of the filtering. So what you need to do is when you design a FOTM network, you need to make sure that you have about 10 gigahertz of spacing on each side to allow the channel maximum throughput. Now, when you put in this FOTM system, you're really going to be limiting yourself to the next generation of optical transport. And when I say that, as we start to increase the baud rate, the channel size increases as well. So if we were to look today at a traditional 400 gig ZR optic, it potentially will not fit in a traditional 100 gig FOTM spacing. And there's several reasons for that. Number one, it's the baud rate and the modulation, as well as you can't go terribly far with it in that type of system because a back-to-back loss is too much for the optic to overcome. Now, looking at overall capacity. So this is really looking at the bits and symbol modulation times the bit rate. So QPSK, if we were to say we were running a 25% forward error correction, you get 4 bits per symbol at 33 gigabaud. It takes about 100 gigahertz spacing. And as you can see, the higher the gigabaud, you're starting to increase the efficiency in the number of bits per hertz, but you're also increasing the channel spacing. So you're taking more spectrum as you increase the baud rate. So this is just kind of giving you a little bit of an idea of the channel spacing versus the spectral efficiency. And as you can see, it looks like at about 90 gigabaud, where you're getting about the most spectral efficiency with current technology. Now, all this is well and good, but what really defines the upper limit on the spectral efficiency? And when I say the upper limit, what I'm saying is how many channels can I really put across the fiber? In 1948, from Bell Labs, Claude Shannon was the one who kind of defined that for us. And this is the Shannon limit is actually different for every individual segment of fiber. And I say that because not all fiber has the same characteristics. Yes, I'm buying SMF28 or I'm buying G655-3AB. You know, there's always impurities in the fiber. Your ILA or inline amplification spacing is not going to be exactly the same on every network. So every network is going to have a different Shannon limit. And with the technology that we have today, using several techniques, we are coming close to being able to come very, very close to hitting it. Now, the biggest problem or the biggest challenge we have is the optical to signal noise ratio. And when you look at that, that's a buildup of noise through the inline amplifiers. Kind of think about it as your car stereo. You're sitting in your car, there's a song that you like, and you kind of play it at a low level, and all of the instruments are extremely crisp and you can hear them. But then you come to a song that you really, really like, and you crank it up, things start to get muddled and distorted. That's exactly the same thing that happens with an erbium doped fiber amplifier that is used to amplify the signal down the line. That's how you can get thousands of kilometers. The higher you run that amplifier, the more noise it's going to put into the signal, and eventually the receiver will not be able to distinguish the noise from the actual signal it's trying to decode. Okay, so let's look at a couple of use cases. Well, the drivers for scalable and sustainable and IP transport solutions. So broadband internet, high definition video streaming, you know the business cases. And the government, with its current round of BEAD funding, is saying that if you don't get 25 in 100, you're an underserved community. So where I live here in Texas, I get 18 and 2. So by the government's definition, I am an underserved for broadband. Now, if the pandemic would have happened a few years ago when my kids were still in school, I would probably have a problem. When my wife working, myself working from home, the kids trying to be on the internet and Zoom calls for school, that would be quite a bit of a concern for us. But anyway, it's just an empty nester, so that 18 meg works great until I can get higher. And when we look, concentrated data traffic growth across the metro and regional network. Okay, so when we start to look at it, we are now putting the cloud a bit closer to us. So when Netflix originally kicked off, they were hosting from a couple locations, and you had to kind of have a little bit of buffering time to get things up and running. Now they've got several caching locations, so it kind of speeds up the transport and also drives up the requirement for increased bandwidth across the network. Sustainability. You know, I was at a conference last month, and in the telecom space, 42% of the respondents said that they were ready to quit, and 25% of the respondents are ready to retire in the next 4 years. So not only sustainability versus the environment, but also staff. We have a case study, an example where the company, the carrier was putting in 10 gig in the access, and it was just growing substantially, which was causing several truck rolls just to do the same turn up. So you would put a truck roll to the end user, plug that up, may have to do some fiber splicing, and then to the access on ramp to the WDM network. What they found is they could actually reduce cost by going to 100 gig on the access. Going to 100 gig allowed them to make a single truck roll out to the edge to actually turn that circuit up, and then it was already had enough bandwidth through the access layer to get into the core. So kind of sustainability on the stack, helping them simplify what they had to do on a day-to-day basis. So made a lot of sense for them. And then also, if we were to look at the new pluggable optics, if we kind of go back and kind of think about the evolution, coherent optics originally were developed in 1999 by Bell Labs in what they call a HERO experiment. They ran 100 gig coherent single channel from Fort Lauderdale to Tampa Bay. And I'm sitting in a room that's probably 15 by 20, and it was full of equipment. Today, that same technology is in the QSFP form factor. Now, we didn't get there overnight. We commercially, as an industry, launched the first 100 gig coherent single channel, 100 gig receiver, transmitter, if you will, in 2010. And since then, things have just gone up and up in scale and smaller in size and footprint. So when we kind of think of what we had in 2010, kind of a monster footprint, which equates to monster power consumption, monster heat, high electric costs and all that. So really what we're looking at is put the optics, the new 100 gig ZR, 400 gig ZR plus directly in the routers or the PON equipment and run it into an open line system. And Nokia, as well as the other optical vendors, are really, really looking heavily at doing that. So over on the left is the conventional way of doing it, where you've got your router sitting there and you put just traditional gray optics in it and run it into a transponder and then over an optical line system. What we are really seeing is on power consumption and space savings is putting that coherent pluggable directly into the router and run it through an open line system. And when I say an open line system, so we're getting the transponder out of the way and just going direct into a amplification system. That's basically what an open line system is. So that's all great, but there are times where you still need to have a traditional transponder. But in the middle mile that we're talking about to extend the broadband out further and further into the network, we believe that the 400 gig or 100 gig coherent pluggable directly into the PON system, as well as the router, are going to provide significant cost savings and power advantages to those who do it. So if we were to kind of look at what are all these different optics? Well, you know, the shiny kid on the block is the 400 gig ZR and the 400 gig ZR plus. And I say it's the shiny kid because we look at the 400 gig ZR plus and it has a capacity from 100 gig to 400 gig, and it's a QSFP 56 double density size. So what that allows us to do is put in an optic and optimize it for the bandwidth that we require across that link. So it also has fairly good distance. Now, here we're saying up to 500 kilometers point to point. We've just completed some modeling for a customer, and we were able to go about 480 miles with the ZR Plus optic directly in their router through an open line system. Now, if we need to go a little bit further than that, then we would look at the next one up to 400 gig multi-haul. And when we say multi-haul, we generally mean a DCO, a digital coherent optic. So what that means is the DSP is built directly into the pluggable, and it's a little bit larger, which means that the DSP can have a bit more functionality. And you kind of think, well, what does a DSP need to do other than decode the signal? Well, when we start to look at these distances, chromatic dispersion becomes an issue, and that can be integrated into the DSP long as there is enough form factor to do so. Now, if we really need to go cross country, but for our analysis today of looking at just middle mile, we may find that a transponder is still the way to go. Pardon me. So when we look, so we'll go back to 2000 SFPs, 10 meg, and what we're at now is at an inflection point. The 400 gig E ZR plus really has the same port density as the QSFP 56, the standard 400 gig data center interconnect. So we've hit a inflection point to where now it makes sense to not go through a transponder type system anymore. It may make sense for the middle mile just to run right out of the PON gear into an open line system and then out to the, I'm going to call it the internet service provider where the BNG is located. Now, Nokia is like all other optical vendors, we're looking at it and we're running case studies across it. So in this case study, what we're doing is we're just using the ZR ZR plus technology directly into a filter and then through a line system. Now, the success or the key to success of this is to make sure that we have open APIs on the router so we can understand what the QSFP is doing for us. Now, here's one a little bit more complex, because we are running a combination of transponders as well as just straight ZR plus and CFP2, but we are doing some, I'm going to say, router bypass. Now, this is a scenario that we see in obviously today using transponders, not the 400 gig ZR plus, but doing the router bypass if you were doing an open line system or an open carrier network. So it's my fiber, I do wavelengths, and I allow anybody or everybody to put their own PON gear, and I give them a wavelength, so it allows me to drop some of the PON gear out and bypass others. So very popular application. We believe this will be a significant footprint and power consumption savings by going down this path. Now, we're kind of thinking, oh, you're talking 400 gig. Well, that's true. That's where we are today. But we need to start looking at tomorrow. Everybody likes the shiny new toy, and 400 gig currently is, but when we look at the 400 gig forecast from when we started looking at it at 2020, as we can see, the 800 gig is now ramping up at going to be a significantly higher level. And when we kind of look at it, the 40 gig, I had another chart in here I took out with 40 gig, and 40 gig just pretty much flatlined as soon as 100 gig coherent optics came out. But here, I think there will be a transition point. But I just wanted to kind of talk to you today a little bit about making sure that we understand how the baud rate affects the network, and also really affects the network architecture the way we want to build it. So with that, I want to say thank you very much. I appreciate your time today, and I am going to put in a shameless plug. Please make sure you join us at Supercomputing 22, where Internet 2 will be there and Nokia will be there as well with a booth and some live demos. So thank you very much.
Great. Thanks, Tim. Very interesting. Feel free, if anyone has any questions, to put them in the chat, and Tim can respond to them, or any thoughts or for discussion. But meanwhile, Tim, have you seen evidence that we really need that 400 gig, or what you're anticipating to be 800 gig within the middle mile networks? Are you seeing evidence of that need already, or are we anticipating?
No, we are seeing that need already. When we have a few open access providers, and they are I'm going to say within a year of providing the access, they are significantly over 400 gig today. So it's happening, and now they are, I'm going to say, primarily focused on longer distances. So the 400 gig ZR plus across the open line system would work well, because most of their networks are from the edge user to the data center is less than 400 kilometers. So that is a business model we are looking at with them.
Very good. And if I understand correctly, it's a bit of an architecture change. So what are some of the nuances of implementing 400 gig ZR or ZR plus optics directly from the router into the optical line system?
Yeah, thanks. So that's a great question, because it is a significant shift in the way that the networks had been built in the past. When we look at that, it is now where there has to be optical and IP integration in communication. You know, when we look at the current generation of ZR plus optics, they transmit -10 to -5 dB, which is a bit hard for an amplifier to handle. So you go through a filter and you're coming in pretty low. So you need to be able to, through an open API in a management platform, say, hey, can you turn that up just a little bit? I need a little bit more light coming out of you. And likewise, when it comes down from the optical side into the router, there needs to be coordination on that as well. So it's a bit of a change in dynamics, if you will. It's putting the IP and the optical network in a more centralized focused, rather than having them as, you know, you do this and you're just a layer one dumb pipe. They now have to interact a bit more for the ZR optics to become successful.
Yeah, that makes sense. So we do have a question in the chat. What is the percent of energy saving with WDM optics versus the gray optics?
So that's another great question. So I did have a slide on that. And when we go back, I'm not going to go back with y'all, but I'll go back myself and take a quick look. You know, a traditional gray optic 400 gig is probably going to be in the, or let's go 100 gig. 100 gig is generally in the 3 to 5 watt range, where a 400 gig is in the 5 to 7 watt range. And if we look at a 10 gig, you know, it's maybe 2 watts. So realistically, you know, by the time you grow a 10 gig network to a 10 by 10 or 100 gig, you're actually exceeding the power consumption that a single 100 gig would have provided to the network. So that's why we see significant savings. And then if we're to come directly out of the optic, the ZR plus optic, in bypass a transponder in a traditional WDM system is probably anywhere between like 120 and 140 watts. So significant savings by changing to a direct connect coherent optic in the router to a line system.
Good. We have another question. Are the APIs between the open line and the router being standardized by some industry group?
We're trying. Let's put it that way. You know, when you look at like the Open ROADM, that is a organization that has worked very hard to make sure that the command set, the APIs for a Nokia router will work with the competitors' routers and all that. So the answer is yes, and the interop standards are there. At OFC last year, we showed this concept using our equipment with I'm not going to say competitors, but another vendor's piece of equipment at the other end. So it's being worked on, and like with any standards, it's going to take a while, and it's going to take collaboration between all the different vendors.
Very good. Any other questions for Tim? Well, I would echo Tim's plug to stop by at Supercomputing and see Nokia, and as well as visit us at Internet too. So thanks, Tim, for the information today, sharing with us today. Thanks to all of you for joining us. We hope you found the session valuable, and a reminder that this event was recorded and it'll be posted along with all the presentation slides on the i2 Online website. So if you have further questions, please reach out to us. Our next webinar, the third in the 3-part series from Nokia, will be on November 9th, when the topic will be 5G Advanced and Outlook on 6G. So information on all of our upcoming webinars is on the Internet 2 events page at internet2.edu/events. And one more time, thanks, Tim, for your time today and for sharing with all of us. So,
Thank you.
have a wonderful day.